In section 4, we're going to talk about what it means to prove triangles are congruent. So we talked about how triangles are congruent, but there's a way to prove it as well. The first one we're going to talk about is angle-side angle congruence. So what that states is if two angles and the included side of one triangle are congruent, to two angles and the included side of another triangle, then the triangles are congruent. And instead of having to write angle side angle out, we usually abbreviate it ASA, which stands for angle side angle. So if I look at the two triangles off to the right here, we have angle T congruent to angle G, angle R congruent to angle C, and then the side between those two angles in each triangle, TR, is congruent to CG. So that would be angle side angle congruence. Next we have angle side congruence, which states if two angles and a non-included side of one triangle are congruent to the corresponding two angles and a side of a second triangle, then the two triangles are congruent. And similarly, we abbreviate it with the letters, so that would be AAS for angle side. So looking at our two triangles JKL and CAB, we could see angle K is congruent to angle A and angle L is congruent to angle B, two angles next to each other, but KJ is congruent to AC, which is a non-included side. So it's a side next to one of the pairs of congruent angles. So let's go ahead and look at a few examples where we can use these congruences to prove two triangles congruent. So we know that AB bisects our angle CAD and angle 1 is congruent to angle 2. We want to prove triangle CAB is congruent to triangle DAB using either angle side angle or angle side. So let's start by drawing our two columns. The one on the left is for our statements, and the one on the right is for our reasons. So we always start with what we're given, and we're given two pieces of information. That AB bisects angle CAD, and angle 1 is congruent to angle 2. And both of these pieces of information are given. So let's go ahead and, before we work on any part else of our proof, let's go ahead and use the fact that AB bisects our angle CAD. So when a segment bisects an angle, it creates two congruent angles. So that tells me that angle CAB is congruent to angle DAB, and that comes from the definition of an angle bisector. And we can go ahead and label that in our picture. So those two are congruent. We're also given angle 1 is congruent to angle 2. So we can mark those as congruent in our picture as well. So if we look at what we currently have, we have two angles congruent, and all that's left is a side that's congruent in each of our triangles, since both congruent statements we've talked about involve a side. There's not enough information to say anything about side CA and AD and side CB and DB, whether or not they're congruent. But both triangles have side AB in common, and by our reflexive property, we know that a side is congruent to itself. So we can say that AB is congruent to AB, and that would be by the reflexive property. So if I go ahead and mark this side congruent, I now have two angles and then the side that's included between those two angles. So I now have enough to say that triangle CAB is congruent to triangle DAB, and the reason would be side angle. Would be angle, side angle. So in the next proof, we're given that AD is parallel to CB and angle A is congruent to angle C. And we actually want to, this labeling is wrong since we don't have G at all in our shape. We want to prove that triangle DAB is congruent to triangle BCD, since those are the letters we have. So let's start by creating our two columns. We have statements and reasons. So start with our given. AD is parallel to CB and angle A is congruent to angle C. So that's our given information. I'm going to go ahead and label angle A and angle C being congruent. If I also look, both triangles have side BD in common. So like in our previous proof, I can say that BD is congruent to BD by the reflexive property. Now all that we're missing is another angle, and we aren't going to be able to use angle side angle here since the side that we have congruent is not going to be between two angles. So that just leaves angle angle side. So we either have to show that angle CDB or angle CBD is congruent to one other angle in our other triangle. And that's where the parallel lines comes from. If I know AD is parallel to CB, I can think of my segment BD as the transversal, two parallel lines cut by a transversal, which means I can use those angle relationships to show that two angles are congruent. And I'm going to say that angle CBD is congruent to angle ADB. Let's go ahead and identify those angles. So CBD is congruent to angle ADB. And then the reason for that would be because they are alternate interior angles. So the reason would be the alternate interior angles theorem. So now I have two congruent corresponding angles in each triangle and a non-included side. So I can now say that triangle DAB is congruent to triangle BCD, and it would be by angle, angle, side. So in this last example, we're going to write a proof to show that VR is congruent to SR, given that angle V is congruent to angle S and TV is congruent to QS. So we aren't actually proving the two triangles congruent, but we will use triangle congruence at some point in our proof. So we set up our columns. We have our statements and our reasons. So we go ahead and state what we're given. Angle V is congruent to angle S, and TV is congruent to QS. That's our given, which is labeled in our picture. So if you remember, if two triangles are congruent, all of their corresponding angles and sides are congruent as well. So if I can show that triangle TVR is congruent to triangle QSR, I can then say that every corresponding side is congruent as well. And I'm almost there because I already have one angle congruent and one side. And if I look, angle 1 and angle 2 are vertical angles, which we know from a previous section that vertical angles are congruent as well. So I can say angle 1 is congruent to angle 2. That would be by the vertical angles theorem. So if I label that, I now have two angles and their non-included side being congruent. So by angle, angle, side, I can say that triangle TVR is congruent to triangle QSR. Now that the two triangles are congruent, corresponding sides and angles are congruent as well, which means TR is congruent to QR, and it also means that VR is congruent to SR, since those are corresponding sides. So I can now say that VR is congruent to SR. And my reason, instead of writing out corresponding parts of congruent triangles are congruent, I'm going to abbreviate it as CPCTC. And we're done because we've proven that the two sides are congruent. So there are a couple more congruences. The first one being side, side, side congruence. So if the sides of one triangle are congruent to the sides of a second triangle, then the triangles are congruent. And we use the abbreviation SSS for side, side, side. So what this means, it doesn't mean that all three sides are congruent to one another in each triangle. It just means corresponding sides are all congruent. So if we look at our picture, we see that AB is congruent to ZX, BC is congruent to XY, and AC is congruent to ZY. So because all three corresponding sides are congruent, the triangles have to be congruent as well. And then we have side angle side congruence, which says if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, then the triangles are congruent. And we're going to abbreviate this SIAS for side angle side. So it's very similar to the angle side angle congruence, except instead of two angles in the included side, it's two sides in the included angle. So if we look, we have side AB congruent to FD and BC congruent to DE, and then their included angles, angle B and angle D, are also congruent. So then the two triangles would be congruent as well. Let's go ahead and use these two congruences in a few examples. So in this first example, we're given EI is congruent to FH, FE is congruent to HI, and G is the midpoint of both EI and FH. We want to prove the triangles FEG and HIG are congruent. Let's go ahead and set up our columns. We have statements and reasons. So we have a lot of given information. We know that EI is congruent to FH, FE is congruent to HI, and we know G is the midpoint of EI and FH. And this is all given information. So let's start by labeling what we know. So I know FE and HI are congruent. I know the entire segments FH and EI are congruent, but considering those go across both triangles, I'm not going to label the entire segment. But what is helpful is the fact that G is the midpoint of EI and FH. So if you remember, definition of midpoint says it creates two congruent segments. So that tells me that FG is congruent to HG. It also tells me that GI is congruent to GE. That would be because the definition of midpoint, and because I knew that EI and FH were congruent, it also means that all of these segments are congruent as well. So now if I look, all three corresponding sides of my two triangles are congruent, which means I can say my two triangles are congruent by side, side, side. So we have triangle FEG is congruent to triangle HIG by side, side, side. So in our second example, we are given that DE and BC bisect each other, and we want to prove triangle DGB is congruent to triangle EGC. Set up our two columns. Our statements and reasons. And start out with our given that DE and BC bisect each other. Which is our given information. So remember, the definition of a segment bisector is that it creates two congruent segments. So I now know that DG is congruent to EG and BG is congruent to CG by the definition of a segment bisector. So DG and EG are congruent and BG and GC are congruent. Now, in order to use side, 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 I'd have to know some information about sides BD and EC, which I don't. So I can't use side, side, side here. So that just leaves us with side, angle, side. So I have to be able to say something about angle BGD and angle CGE. Well, since I know BC and EG are two intersecting lines, that would make those two angles vertical, which means they are congruent. So I can say angle BGD is congruent to angle CGE by the vertical angles theorem. If I look, I now have two sides and their included angle congruent, which means triangle DGB is congruent to triangle EGC by side, angle, side. So in our last example, we are given that AB is congruent to AC and BY is congruent to CY, and we want to prove triangle BYA is congruent to triangle CYA. Set up our columns. with statements and reasons. So I just start with given information. So we know that AB is congruent to AC and BY is congruent to CY. So I label that AB congruent to AC, BY congruent to CY. Now, I'm not given any information about any of the angles of our two triangles, so I can't use any proof that involve any congruent statement that involves angles, which just leaves us with side, side, side. So I have to be able to say that AY is congruent to AY. Well, considering it's a shared side in both triangles, the reflexive property says that a side is congruent to itself. So I can say that AY is congruent to AY by the reflexive property. And I now have all three corresponding sides of the two triangles congruent, which means triangle BYA is congruent to triangle CYA by side, side, side. So make sure when you're writing proofs for two triangles being congruent that you start with what you're given. It's always a good idea to label that in the triangle. And if you're given a midpoint or a bisector of some sort, always use this definition in your proof so that you know where to head with what congruent statement to use. There's usually only one way to go about proving two triangles congruent based off the given information. So make sure you use that information when you're completing the assignment. And as always, make sure you ask for help if you have any questions.